All right, well, let's move on to the second lecture on refrigeration, lecture 28, section 10.4 in chapter 4, in chapter 10. And we'll talk about cascaded and multi-stage refrigeration systems. Basically, once again, first we gave the general principle of this basic cycle, and now we're going to look at means to improve the efficiency, which in this case means decrease the amount of work one has to put in the compressor to get the same amount of refrigeration. So the first technique used is called the cascade. Well, the cascade is actually not designed to improve the efficiency. It's designed to lower the minimum temperature. And you will actually use this if we do this project on liquefying gas. If you have to liquefy something, you have to have a low temperature that is that's very low, much below what you can get in a single stage. So this is something that's used when the refrigeration is needed at low temperature, and what there is here is an intermediate heat exchanger. So basically, you have a low temperature cycle where you have the useful heat that's taken out of your system in a low temperature evaporator. Then, so here you have a first fluid, the low temperature fluid in cycle A, the isentropic compression, the intermediate heat exchanger, which is in fact the condenser for this cycle A, but at the same time, the evaporator for cycle B. So we have the condenser here, then we have the expansion valve for the low temperature cycle, and here we have the evaporator that extracts the heat on the low cycle. So here we have an intermediate temperature, and cycle B is a high temperature cycle. So you have another fluid that goes from 5 to 6 in the compressor, rejects the heat at the higher temperature, for example, room temperature, goes to an expansion valve, and then pumps heat out during this evaporation step here. The evaporator here pumps heat out of the condensation of cycle A. So now the overall system, the overall heat in is Q dot in is at the low temperature evaporator, and the overall heat out is Q out is at the high temperature condenser, and this is the intermediate one. So this is needed when you need very cold temperatures. And it's a general principle that you can use with many other type of refrigeration cycles, for instance, in Brayton's or absorption cycles or thermoelectrics. They all use cascades in different stages of the cascade, stage A, stage B. So let's go into the details of how this works. If we look at cycle A first, only the low temperature cycle, you have the equations, which is Q in here, plus the work that you put in the compressor on the low temperature cycle is going to be Q out, which is the heat that's transferred, transfer between cycle A and cycle B. So it has a certain COP sub A, which is Q in over the work that is taken into compressor A. Now cycle B has as Q in this heat exchange, the X transfer. So this heat plus the work done in compressor 2 is what's going to be the heat that's rejected Q out in the high temperature condenser, and it has its own COP. This third equation that matters is the heat balance and the mass balance in the heat exchanger. So of course the mass balance is M2 equals M3 and M8 equals M5. But the heat balance is that if you look at MA, H2 minus H3, that's the enthalpy in, must be cycle B, this is a mistake, H5 minus H8, this is MB. So in the cascaded cycle, then, you have a net COP, which is, of course, Q in, this is useful heat, divided by the sum of the work that's input in A and in B, it's here, and that necessarily is smaller than the COP of either A or B taken separately. So cascaded cycles have a lower COP than individual cycles, but they reach much higher delta T's. That was step number 1. Step number 2 is what we do to increase the efficiency. So to increase the efficiency, we have what's called multi-stage vapor compression intercooling. So essentially, this is the basic same concept as we used in the intercoolers in Brayton cycles. But the problem is you can't make an intercooler in a cooling cycle because you already are below room temperature. So there's nothing you can dump your heat into. So the trick here is quite different. It makes use of something called a flash chamber. A flash chamber is something that separates saturated vapor from saturated liquid. So you have something here that's a mixed inside the vapor dome at point number 6. This has a certain quality to a mixture of vapor and liquid. And then you let gravity condense your liquid to the bottom, and gravity make the vapor go to the top, and you recycle the vapor here, and you take the liquid out to a second stage. This, of course, only works if you hold that thing vertical. If you put it on its side, or if you turn it upside down, it doesn't work. So some refrigerators have this mark that you can't turn them on and for 24 hours or something after you have shaken them. That means they have a flash chamber. Gravity has to get the liquid out. Okay, so now we're going to reconstruct this TS diagram step by step. So first of all, the reason we use this bizarre thing, flash chamber and direct contact heat exchanger, is because, of course, this is the heat at room temperature, so you can't use intercoolers, but the principle is the same. You are going to make this thing behave as if it were an intercooler, except you can't cool below room temperature. So basically what you're doing is you're cooling cycle B with heat from cycle A, if you want to look at that this. You're cooling cycle 1 minus X with heat that comes from cycle X. But now the goal is not to go to lower temperature, but to have a better COP. So the two steps, the direct contact heat exchanger, which mixes the fraction of the vapor that comes from the flash chamber, fraction X, with fraction 1 minus X that comes from the lower temperature part of the cycle, the liquid part of the cycle, through the first compressor. So that here you have the total fraction of the mass flow, that's again Mars. Now, the flash chamber is part number 1. In comes the mixture, as I explained before. The vapor goes into 9 and the liquid goes into 7. The quality of X6, this determines what the fraction is that goes as X and the fraction is goes as 1 minus X. In fact, this quality has to be X, and 1 minus X then is the liquid fraction. This arrangement decreases the compressor work a little bit like an intercooler does, but I haven't proven that to you yet, so that comes next. So let's go look at the TS diagram of the process. So first, we start, let's say, at point number 1 here. So this only fraction 1 minus X goes through this compressor, and fraction 1 minus X goes from 1 to 2. Now here, that here in 2 is cooled by liquid that gets mixed to it, vapor that gets mixed to it from point number 9. So number 2 is lowered in temperature. This is the temperature axis, which got cut off. Is lowered in temperature from 2 to 3, from 2 to 3. So the heat in 3 is lower than the heat in 2, but it's higher than the heat in 9, the temperature. In 3 is higher than the temperature in 9, but lower than the temperature in 2. And then you go through the second compressor, that's like before. And then you go through the condenser out here. You have the first expansion valve, 5 to 6, gets you here. The quality at 6 is what determines the fraction that goes here and the fraction that goes there. So 6 to 9 goes here, and 6 to 7 goes from the bottom of the flash chamber into the second expansion valve, where it gets made into a mixture, again, of liquid and vapor, but at a much lower temperature. That's point number 8, which then goes to the evaporator that uses the useful Q in. And since, of course, the work done into the system is the area of these curves here. So, I lost my mouse. The work is 1 to 2 to 3 to 4 to 5 to 6, 7, 8, 1. You see that work is decreased vis-a-vis what it would have been had we gone all the way up to A. So that is the useful part of the intercooler. It decreases the compression work. The flash chamber, like I said, is used to separate the mixture. And so it goes 5 to 6. It sends 6 to 9 this way, and 6 to 7 through the bottom, so that the second nozzle only has pure liquid to expand. And then the direct contact heat exchanger does bring everything back together, but of course, both here and here, the pressures are the same. So P2 equals P9 equals P3, and P9 equals P6 equals P7. So all these pressures are all here, 6, 7, 9, and 3 all the way up here, 3 and 2, they're all the same. And I now have to write the equations. So let's go into the flash chamber. First, we have the conservation of mass. So M9 plus M7 is what comes from M6. And then we have the conservation here of mass means that X, which is M9, is the mass of the total gas that comes in here. So let's say this is M dot. M9 comes out X, it's M9 over M. And of course, X7 is 1 minus X times M. So M total minus M9 is M. It's just M7 over M dot. That's the fraction X. Basically, this fraction X, as we said before, is the quality of the steam, the quality of the mixture at section 6. That means then you can write your equation of balance, energy balance, and mass. So the total mass times H6 equals the fraction that comes out times the enthalpy, H9, plus the mass, 1 minus X, fraction, times H7, that comes out at 0.7. This now is the energy balance, and this is what happens on the flash chamber. Let's repeat the same exercise on the side of the heat exchanger. So M9 plus M2 equals M3, and M3, of course, is the total flux flow, which means that the conservation of mass equation, that's not fantastically difficult. X plus 1 over X is 1, plus 1 minus X is 1. And we write the energy conservation again. So we have X times H9, which is the enthalpy that comes in here, 1 minus X times H2, sum these two, that is simply going to be 1 times H3, and these are now your two equations of conservation, which you will use into your problems. Now we can write the full set of equations for the full cycle. So look at the cycle macroscopically. The heat in, the useful cooling capacity of the system, well, its mass flow rate being the mass flow rate through here, times 1 minus X, because only fraction 1 minus X goes through the evaporator and extracts useful heat, times H1 minus H8. That's this. The heat rejected is the full mass flow rate, so it's 1, times H4 minus H5. The work put in the turbine, in the low pressure compressor, the low temperature compressor, is the mass flow rate, which is 1 minus X, times the change in enthalpy, H2 minus H1, that's this equation, and the work into the upper compressor, upper here in temperature, is the full mass flow rate, so 1, H4 minus H3. And the diagram looks like what it looks like here. So we have the governing equations: conservation of energy in the flash chamber, conservation of energy in the direct contact heat exchanger, all your enthalpies in your useful condenser and evaporator, compressor and compressor, they're all here. Of course, your expansion valves are just isenthalpic transformation, H5 equals H6 H7 equals H8. And this one additional equation here, that is that the value of X here has to be the same as the quality of the liquid vapor mix at 0.6. And with that, you can solve all your equations, get your COP, and you're done. Thank you.